Now we move forward and define the concept of extremum of a function. So this is the maxima and minima of functions. Maxima and minima of functions. First of all, we define what we mean by this maxima and minima. So here we have a definition. This is a function y equal to f of x has a local maximum at a point, suppose x equal to some point c, if f of c is greater than or equal to f of x for all x in the domain of f. So therefore this point c, it is a point of local maximum if this f of c is the largest value of f of x for all values of x in the domain of f. And on similar lines, we can say a function, suppose f of x has a local minimum at x equal to c if now this f of c is less or equal to f of x for all x in the domain of f. So therefore, if f of c is the smallest value of f of x in some particular domain of f, then we call this c is a point of local minima, and f of c is the local minimum value. And similarly, if f of c happens to be the largest value of f of x for all the values of x in the domain of f, then we say c is the point of local maxima, and f of c is the local maximum value of f. We add a little more here. So this is one remark. If f of c is greater than or equal to f of x for all x, then c is called the point of local maxima, and f of c, which is the value of function at c, is the local maximum value. And similarly, if f of c is less or equal to f of x for all x, then c is called the point of local minima, and f of c is the local minimum value. Now let's try to understand these local minima and local maxima graphically. So here we construct one random curve. Suppose this is the x-axis and this is the y-axis. Now let's try to make a curve like this. Okay, so assuming that this is the point A here, and suppose this is the point B here, and we take this curve from A to B. Now in this curve we can see that if we look at this point, so and this vertical distance, then this is suppose the point x naught, then this vertical distance, which is defined as f of x naught, we can see this is the largest value of f of x throughout the domain from A to B. And similarly, if we look at this point like this, suppose let's call this point as x1, then this will be the value f of x1, and we can clearly see f of x1 is negative because it lies somewhere here, and this is below the x-axis, so this is negative. Now, what we mean by local maxima and local minima? Now, similarly at this point, we can say this is suppose the point, let's call it x3, then this is the value f of x3, which is again negative. And similarly, if we suppose look at this point, this is suppose the point x4, and now this value is f of x4. Now if we look into this function from A to B, then f of x naught is the largest value of f from A to B. And similarly, we can see this f of x1, which is here the point, this is the smallest value of f from A to B. Now when we are trying to define the local maxima or the local minima, we will not take the curve throughout the domain. Suppose we want to find the local maxima or local minima, like from this point up to suppose this point. Let's randomly choose these 2 points, and let's call these 2 points as suppose P, Q. So suppose from P to Q, we want to find the largest value of f and the smallest value of f. Then from P to Q, we can see that x0 is a point where the function f has the largest value and x1 is a point where the function f has the smallest value. So therefore this point x0 is a point of local maxima on the interval p to q, and x1 is a point where the function has the smallest value, so x1 is a point of local minima on the interval p to q. And again, this f of x0 is the local maximum value on the interval p to q, and f of x1 is the local minimum value on the interval p to q. Now again, if we suppose take up a different points, suppose we take some point here, which is suppose some point r, and we want to look for the local minima and the local maxima on the interval r to p. Then we can see this point, which let's call this as point x5 now. Then this x5 will be the point where the function has the maximum value, which is positive here, and x3 is a point where the function has the minimum value on the interval r to p. So therefore on this interval from r to p, the local maximum value is obtained at x5 and the local minimum value is obtained at x3. And in fact, throughout the interval a to b, the local maximum value is obtained at x0 and the local minimum value is obtained at x1. Now one more property that we can look into these extreme points. Let's explain that in the next graph. Let's again consider one graph randomly. So suppose this is the point A and suppose this is the point B, and we are defining our function from A to B. Now from this graph we can obviously see that the points where the function could have the smallest or the largest value, it is first of all this point. Let's call this point as x0. It may be this point. Let's call this point as x1, and similarly maybe this point which is x2, and similarly this point, let's call this point as x3. Now these are the only 4 points where a function can assume a maximum value or the minimum value. Now all these points have one similar property, that if we draw a tangent to the curve at these points, like suppose if we draw a tangent to this curve at x0, it's a tangent like this. And similarly, if we draw a tangent here at this point, it is a tangent like this, and similarly a tangent at this point, so it will be touching this curve at this point, and similarly a tangent at this point, so it touches the curve at this point x3. Now all these 4 tangents have one similar property, that they are parallel to x-axis, or we can say that these 4 tangents have one similar property, that their slope is equal to 0. So we can say, so all tangents, so the tangents at the points where a function could assume an extreme value. An extreme value here means a value which is either minimum value or the maximum value. The tangents at the points where a function could assume an extreme value have slope equal to 0. Because these tangents must be parallel to x-axis at these points. But we also know that the derivative of a curve actually represents a slope. So therefore we can think of finding these points in terms of derivative of a function. So now here we take the question of how do we find these points on a curve, and then how do we understand and evaluate which of the points is a point of local minima or which of the points is a point of local maxima using the derivatives. So this is working rule for finding the extrema. Now the first step that we have to do here is find critical points. So what are critical points? These are the points where first derivative becomes 0 or undefined. That is, we will have f dash of x is equal to 0 or f dash of x does not exist. So this will be our first step. Now the second step is, so once we have equated this f dash of x equal to 0, suppose we obtain a singular point or a critical point x is equal to some point A. Then let's proceed towards the second step. Then we evaluate, we find this f dash when x is slightly less than A, or we can say f dash at A minus 0, and we evaluate f dash at A plus 0. So this is, we have to evaluate the left hand limit of f dash at A and the right hand limit of f dash at A. Now if this left hand limit becomes positive and right hand limit at A is negative, then this x equal to A is a point of local maxima. And second, if the left hand limit of f dash at A happens to be negative and right hand limit of f dash at A becomes positive, then x equal to A is a point of local minima. So this is the point number 2, the step number 2. This is known as the first derivative test. So therefore this whole thing is known as first derivative test. So in the first derivative test, what we have to do, we first evaluate f dash of x equal to 0 and find the critical point as x equal to A is suppose a critical point. Then we have to analyze each critical point one by one. Suppose we choose a critical point x equal to A, then we evaluate the derivative of f when this x is slightly less than A, and we evaluate the right hand limit of f dash at A. If the left hand limit is positive and the right hand limit is negative, then the point x equal to A will be called a point of local maxima. But if the left hand derivative at A is negative and the right hand derivative at A is positive, then x equal to A is a point of local minima. So now let's proceed towards defining the second derivative test. So this is point number 3. So this is the second derivative test. Now in the second derivative test, what we have, so let x equal to A is a critical point, which is obtained in step number 1 if the second derivative at A is greater than 0, then x equal to A is a point of local minima. So if the second derivative at A is positive, then x equal to A is a point of local minima. Now if second derivative is less than 0, then x equal to A is a point of local maxima. And third, if f double dash of A is equal to 0, the test fails. So therefore the second derivative test has the property that if the second derivative at a critical point is positive, then that critical point will be a point of local minima. If the second derivative at a critical point is negative, then that critical point is a point of local maxima. And if second derivative is equal to 0 at a critical point, then the test is inconclusive, that is the test fails. Now we can proceed towards using these tests in the examples. Now let's take an example here. So we have these two examples here. We will evaluate the local maximum and minimum values of these functions at their critical points. Now let's take up their solutions. First let's take up the solution 1. So we are given f of x is equal to x cubed minus 6x squared plus 5. Then first of all we evaluate f dash of x. So then f dash of x is equal to 3x squared minus 12x. Now put f dash of x equal to 0. We obtain this 3x squared minus 12x equal to 0. Then this implies this 3 into x squared minus 4x is equal to 0. So this implies this x into x minus 4 is equal to 0. So this implies x equal to 0 or x is equal to 4. So that means we have obtained two critical points for this curve. Now we will apply both derivative tests for understanding how we use these two derivative tests for evaluating x equal to 0 as a point of minima or maxima, and similarly x equal to 4 as a point of minima or maxima. So first we use the first derivative test. Now in the first derivative test, what we have to do, we have to evaluate this f dash at when x is slightly less than 0 and f dash when x is slightly bigger than 0. So we have this f dash of x. This is equal to 3x square minus 12x, which we can write as 3 into x square minus 4x, or which we can write more simply as 3x into x minus 4. Now let's look at what happens with this f dash of x when x is slightly less than 0. For f dash when this 0, suppose minus some h, where h is a positive quantity. So when we have 0 minus h, that means we have to substitute a negative quantity in this for this x here. If we put x equal to some negative quantity, a very small quantity which is but negative, so this 3x becomes negative. Now here if we again put negative quantity, so this becomes negative minus negative, which is negative. So negative into negative becomes positive. So therefore this becomes greater than 0. And similarly, f dash when this is 0 plus h, so that means we have to substitute some small positive quantity for this x. Now if we substitute one small positive quantity for this x 3x becomes positive, and small positive quantity x substituted here, it becomes a small positive number minus 4, which is obviously negative. So therefore this becomes less than 0. So therefore this is less than 0. That means the left hand derivative is positive and the right hand derivative is negative. So this implies f dash changes its sign from positive to negative. So this implies x equal to 0 is a point of local maxima. Now for point 2, for x equal to second extreme point 4, let's evaluate this f dash of suppose 4 minus h. So this is equal to, now again looking into this function here, if we substituted x a value which is slightly less than 4, so this 3 into x becomes positive. And now here if we substitute a value of x which is slightly less than 4, then slightly less than 4 minus 4, it is negative. So therefore here we have the quantity which is negative. So therefore this becomes negative. And similarly f dash of 4 plus h, and we must mention here this where h is greater than 0 but very small and h tends to 0. Now here similarly, so we pick up h tending to 0 but greater than 0, but h is greater than 0. Then f dash of 4 plus h, so in this value of f dash of x we have to substitute this x as a quantity which is slightly bigger than 4. Then 3 into x becomes obviously positive because 4 plus h will be positive. So positive into 3 is positive. Now here for this x we substitute a quantity which is slightly bigger than 4. So a quantity bigger than 4 minus 4 is again positive, and positive into positive is positive. So therefore this is greater than 0. So this implies f dash changes its sign from negative to positive at x equal to 4. So this implies x equal to 4 is a point of local minima. So we have classified x equal to 0 is a point of local maxima and x equal to 4 is a point of local minima. Now we can evaluate the maximum and the minimum values. So finally the local maximum value of f of x is f of 0, which is equal to, now let's substitute this 0 in the given function. When we substitute 0 in the given function we get 5. So therefore the local maximum value is 5. And local minimum value is f of 4, which is now equal to 4 cube minus 6 into 4 square plus 5. Now let's evaluate what is this equal to. So this is equal to 64 minus 6 into 16, then plus 5. So therefore this is equal to 64 minus 96, then plus 5. So this is equal to 69 minus 96. So this is equal to minus 27. So therefore the local minimum value of f of x is minus 27. So this was how we use the first derivative test for finding the local maximum or the local minimum value. Now on the same question we will also try to understand how do we use the second derivative test. Now using second derivative test. And again in the second derivative test, first of all we have to evaluate the critical points. The critical points are x equal to 0 and x equal to 4 that we have already obtained in the above part. So now let's evaluate the second derivative. Now f double dash of x, this is equal to d by dx of f dash of x, which is equal to d by dx of, now the first derivative was equal to 3x square minus 12x. Now the derivative of this thing is equal to 6x minus 12. Now we have to evaluate the second derivative at both of these critical points. So then this f double dash at 0, this is equal to minus 12, so which is less than 0. This implies x equal to 0 is a point of local maxima, because we have defined above that when the second derivative is negative at a point, then that point is a point of local maxima, and maximum value is f of 0, which is now again equal to 5. Moreover, again this f double dash of 4, now this is equal to 6 into 4 minus 12, which is equal to 24 minus 12, which is equal to 12, and this is greater than 0. So therefore this implies x equal to 4 is a point of local minima. So and the local minimum value is f of 4 that we have also evaluated in the above example, that is minus 27. So therefore we can see clearly that second derivative test is very easy to use, and but first derivative test is little bit difficult to use. But unfortunately the second derivative test has a drawback that it fails sometimes. But now how we have to solve these questions in exam? Sometimes in the examination we will be asked to evaluate the critical points and their local minima or local maxima using the first derivative test. So if it is asked in the question that we have to use the first derivative test, then we have to use the first derivative test only. But sometimes they will ask in examination to use the second derivative test. So then we have to use the second derivative test and evaluate our question accordingly. But sometimes it is not mentioned whether we have to use the first derivative test or the second derivative test, but the question just asks us to classify the critical points of a given function or find the extreme values of the given function. Then in that situation we can use any test. So obviously in that situation we will try to first use the second derivative test, but if it happens to fail, that is if at some critical point we get f dash of a equal to 0, then for that particular critical point we have to switch back to the first derivative test and classify that critical point accordingly to be the point of local maxima or a local minima. Now we have the next example here, which is f of x is equal to x plus 1 by x. Now again here we will classify the critical points to be the points of local minima or local maxima, and for that thing again what we have to do, we will first find the derivative of this f at with respect to x, and obviously the derivative is equal to 1 minus 1 by x square. Then equate the derivative to equal to 0. It will give us some values of x, and those values of x will be the critical points. Then using the second derivative test we have to find the second derivative of the same function and substitute those critical points into the second derivative of the function. So wherever the second derivative test is positive, then that critical point is a point of local minima, and wherever the second derivative is negative, that point is a point of local maxima. But in order to use the first derivative test, we have to find the critical points again and then find the left hand derivative, find the value of the first derivative when x is slightly less than that critical point, and find the derivative value of the derivative when x is slightly bigger than that critical point. So if this sign changes from positive to negative, then it will be a critical point, which is a point of local maxima. But if the value of this left hand derivative and right hand derivative, if it changes its sign from negative to positive, then it will be a point of local minima. So this is how we have to apply these two tests for evaluating a given critical point to be a point of local minima or a point of local maxima. Now, if a particular point happens to be a point of local minima, then the value of the function at that point is the local minimum value. And if a point is a point of local maxima, then the value of the function at that point is a local maximum value of the function.